Welcome to Math 106, Chapter 6.2, where we talk about the definite integral and net change. So back in Chapter 6.1, that previous section, we talked about how to do basic integration. So integration meaning your antiderivative working backwards. And now today we're going to use that knowledge and then go a step further. So it says the definite integral. Suppose that f is a continuous function on an interval a to b with an antiderivative f, that is f prime, is equal to f of x. The definitive integral of f from a to b is the following. So that big takeaway is just saying, hey, we're going to have a as some numerical value all the way to b as some other numerical value. And we're going to take your function and we are going to integrate and then take the difference between b and a once you plug it in. Now, b typically is your larger numbers. Think bigger number minus smaller number. So step one, we have to integrate. And then step two, we are going to plug in b into integration. And step three, we plug in a into integration and then subtract. And that is all it is. Now, typically, right, after we do your integration, we usually add c. Now, when we know your interval from a to b, we no longer have to include c. We end up dropping c. That is because when you go to do the subtraction between that value from a to b, right? So each one has its own, has its own net change, right? So the horizontal change with the vertical change, and then again, the horizontal change with the vertical change. And we said in one of our last examples, right, we talked about C, how we can have lots of different variations of C depending on if we're given a point or not, right? Now that C goes away because you know now the interval of a to b, meaning that when you go to subtract these two, right, if we subtract f of b plus c minus f of a plus c, that notice that when we distribute, we have a plus c and a minus c that will cancel out. So they end up canceling out, and so you end up dropping c. So when you go to integrate, we do not need to do plus c because it has no effect on your integral on this portion of it. So c has no effect over the net change. So we drop c when the interval is known. So if you have the integral of a to b. So let's try out a first example. So let's take a look here. Now keep in mind how you traditionally integrate. That is from your previous example, right? We said, okay, well, typically, right, if we're working in reverse, we're going to add 1 to your exponent. So now we have x squared. We said, okay, now we're going to divide by your new exponent. So we're going to divide by 2. And this is where we said, okay, now we get to add your c. But now because we know a and b, here we have a and here we have b, we can go ahead and drop this plus c. Now what this means is that we can go ahead and enter in when x is equal to 2, and then again when x is equal to 1, and take the difference. So for us here, we have x squared over 2, right? And instead of having x, we now know that we have your first, your a or your b, sorry, b should be 2. minus, and one more time, we take that integral, and this time we're going to subtract 1. So here we have 4/2 minus 1/2, which is equal to 3/2. That is the change, that difference in those integrals. Let's have you try it again here. So looking at this one, when we go to integrate e to the negative t, keep in mind what we learned from your previous section about the integral of e, where we said, hey, this is really, if we just had e to the kx dx, right? Previously, we said, hey, we're going to write it out first, right? That because the derivative of e is itself, so the integral of e, again, is itself. And when we take a look at your k value, right, normally k comes down and we multiply. Instead, k comes down and we're going to divide by k. So for us, and then we can add your c, right? So for us, when we go to integrate e to the negative t, we write itself, and then we get to divide by k. Your k happens to be this -1. So we will divide everything by that -1. And instead of saying plus c here, we're going to use t when it's 1 and when it's -1. Oops, forgot my little negative symbol, -1. There you go. So we have negative e to the negative t, when t, one more time, I'm going to write it out, is 1, and when t is -1. So let's go ahead and see what that comes out to be. So we have negative e to the -1 minus negative e to the -1. Be careful, there's lots of negatives going on here. So you have negative e to the -1st plus e to the 1st power. So this is really e minus 1/e. Now this is your exact value, or the exact integral. And if you wanted an approximate, we can always type this in, right? But this is the exact value. You'll notice that I kind of just swapped those positions. No, they don't end up canceling each other out because this is a negative exponent, which means it has to drop down. So if that was kind of your misstep there, keep in mind you can only combine like terms, terms that look exactly alike. And then down below, one more time, we just kind of talk about why your C cancels. And again, I think I showed that here, where they end up canceling no matter what once you do that full distribution. Now let's take a look at a couple rules. So if we have A and B, right? B, we said, hey, it's typically that bigger number, but we could also have it in the reverse, right? If we went in the reverse value, where we have B down here, your bigger value up there, and A being your smaller, that all that it does for you is that it takes kind of that reciprocal approach where it's just now a negative. So it'll come out with the same exact integral, but it's just over a negative value. Now, if you have the interval where it's the exact same, there isn't going to be any sort of change. So this will end up being 0. That is because when over the same interval, there is no change. And that is what exactly that we're looking for with your integration, is to see, is there any sort of change? Now, just like with your derivative rules, right, we can also apply your integral rules, right? So we could say the sum of integrals, right? Sum of integrals, difference of integrals, and then the constant multiple, right? Where I think we even covered this last section as well, but just to kind of reiterate now with your definitive integral, where we have now a set value over an interval, we can just say, okay, well, we're going to break these apart. We have the derivative, not derivative, the integral of f of x, that is over a and b, plus, because there's a plus sign right here, plus the integration between a and b of g of x. And we can do the exact same for your difference in your integral, because all that is, oops, too big, is now just doing a subtraction sign, because that is what your function first started with. And what these two mean in words as like what we would do for them is that we are going to integrate separately. And again here, integrate separately. Keep your signs the exact same. So if we have addition, we're going to add between them. If we have subtraction, we're going to subtract between them. Now your last one, as we said from your last time, your constant here, or your coefficient here, because k is just going to be some sort of constant, we're just going to kind of kick it out, because it's sometimes it gets in the way of sorts. So we're just going to put it on the outside and continue to integrate as if it weren't there. And then we'll pull it back in when we're ready to start simplifying. Again, this is over the interval of a and b. So this is just to say push coefficient outside and integrate. Bring back when simplifying. Because it won't affect your integral, like the integration portion of it. It will affect your final answer if we wanted just one singular value to simplify. So let's go ahead and try that out with example 2. Now here it looks like we might want to simplify them separately, which if that is what you feel like doing, that is perfectly fine. But look at it from the perspective of, hey, are they going to be over the same exact interval? Notice that we have 1 to 3 and again 1 to 3 here. So if you wanted, you could integrate here, then subtract times 2, and then integrate here, and then kind of take that take the difference between your integrals, right? However, right, notice that if they are underneath the same exact interval, and we're talking about these combination, notice that there's an x and an x, there's x cubed and x cubed, there's going to be some sort of easier form. So what we can do instead is we can put this under one integral as well. And of course, you could do it in the reverse. If there's lots of terms, we can kind of integrate them separately, which we'll see here in a moment. But first, let's see if we can simplify. So putting this all into one, we have 6x minus 18, x cubed, minus 2, x minus x cubed. And we're going to do that full integration here. That is, let's simplify first. So let's go ahead and push that through. Simplify a little bit, and I'm actually just gonna highlight this portion. That way I don't have to keep writing it. So we should get negative 2x plus 2x cubed. And now we can go ahead and simplify, because we have 18 and 2, and then 2 and 6. So one more time, I'm going to paste. So let's see, we should get let's see, 6x minus 2x, that gives us 4x, minus 18 plus 2, so that should be 16x cubed here. And now let me bring those together. So now what we can do is integrate something that's now a little bit smaller. Again, there's nothing wrong with if you want to integrate these separately and then combine at the very end. It's just going to be a little bit more work for you. So, and again, if you wanted to, we could also factor out some like your 4 from both of these and kick it out like you would with your K here. It's not really going to affect any of your values. Well, let's just go ahead and get to this integration portion. So we can add 1, divide by 4, divide by 2. So now we're left with, after simplifying, 4 divided by 2, that's 2, x squared, minus 16 divided by 4, that is 4, x to the 4th, over the integral of 1 to 3. So that is when x is equal to 3 and when x is equal to 1. So let's go ahead and put that through. So we have 2x cubed or 2x squared minus 4x to the 4th minus, one more time, I'm going to just write that out. This is when we have 3, 3, and 1, 1. And let's go ahead and start simplifying. We have 2 times 9 minus 4 times 81 minus 2 minus 4. So we have, let's see, 18 minus 324 minus a negative 2. So let's see, we have negative 306 plus 2 to make negative 304. So that is your change between that interval from 1 to 3. So kind of a step-by-step process to recap what we did. So A, if want to integrate separately, okay. Or step B, part 1, is to combine the integration and simplify. And then over here, we get to integrate. And then step B3, we can go ahead and plug in interval f of B minus f of A. So if we have integrals over adjacent intervals, that is to say, if we have the integral from A to, let's say, C, f of x, d of x, plus the integral from C to C to B of f of x. Notice that instead of doing it into separate parts, as long as there's some sort of a connection, right? We have C here, and then we have C here. We can go ahead and scratch out these two separate and just write it into one integral. That is over the interval from A all the way to B. So what that might look like, let's see, I guess I don't have an example for you. Let me find a quick one. So let's say we have 0 to 1 of 7x plus 4 dx plus 1 to 2 of 7x plus 4 dx. So notice that we have the exact same function here. Let me try that one more time. There we go. The exact same function. we start on a 0, we go up to 1. Then we start on 1 and go up to 2. So what we can do is write one integral between 0 and go all the way up to 2 to evaluate 7x plus 4 dx. That way we avoid having to write it multiple times. So in which case, we can just write, or we can actually just take your integral, right, of, let's see, x squared over 7 plus 4x when x is equal to 0 and when x is equal to 2. So from here, we can say, okay, well, we have 7, 2 squared over 2 plus 4 times 2 minus 7 over 0 squared. Well, actually, if we know that it's over 0, both of these will end up being 0. So we have, let's see, 7 times 4 over 2 plus 8. That'll cancel and leave behind a 2. So we have 14 plus 8. 14 plus 8, 22. So why does this happen? Well, it happens because we're just taking your derivatives in chunks. So it'll just end up allowing us to integrate over one fluid motion versus several different chunks. So now let's have you guys try some extra examples before we wrap it up. So let's see if you can try these next 4. So first thing we want to do is go ahead and integrate. So we can always add 1. And we're just going to add your x, divide by this 2. So we have x squared minus 3/4 x over the interval of 1 and 0. So we have 1 squared minus 3/4 times 1. And if we know that both of these x values contains a 0, so let's go ahead and just subtract 0. So you have 1 minus 3/4. So we can say 4 over 4 minus 3/4. So we have 1/4. Let's try it again over here and pause when you need. So we can add 1, divide by 2, divide by, or in this case, we'll multiply here by 3. So we have x cubed over 9 minus 2 over 18, and this is x squared, over the interval of 2 and -1. So we have 2 cubed over 9 minus 2 over 18, which 2 over 18, I should have just canceled these out really quickly. So I'm just going to write that one out as 9. Then we have, let's see, x squared, so that is 2. This is minus, and that same thing, except swapped with a 1. So no matter what, this is 1/9 minus 1/9, so that will cancel and make a 0. Oh, actually, it's a negative, so sorry. That could change things. That makes it a positive, but that makes it a negative. So the only thing that changes is just the order in which it happens. So that'll cancel. And then we end up having that negative on the outside. So that'll end up being 0 over here. For here, we have 8 over 9 minus 4 over 9. So we're left with 4 over 9. Let me just check that one more time. My apologies. When I swapped it for a -1, I forgot that I needed to put back that initial negative sign instead of canceling it out. So that is going to change ever so slightly. So we should have, and that's coming from here. So if we did the same thing, we had a negative on the outside. We have -1/9, and we have a -1/9 here because, right, that this -1, because it's an exponent of 2, does not really affect your sign. So we should get -2/9. So we have 4/9 plus this 2/9. It's plus because you have the negative on the outside paired with the negative over here. So we should get 6/9. And when we simplify, right, both of these have a 3 in it. So this is equal to 2/3. Let's try it again here. We might want to consider showing the actual power of this one. So again, add 1. This one will divide by 2. This one will divide by 3/2. Now keep in mind, when you divide by a fraction, we end up multiplying by the reciprocal. So your 3's will cancel. So we're left with, on this side, a 2t to the 3/2. And you could always check that by bringing it down to multiply, and you'll get back to the initial. So here we have 2t squared, again, because 4 and 2 simplify. And this is over the interval between 4 and 1. So you can say 2 times 4 to the 3/2 plus 2 times 4 squared. That's your first chunk. Minus 2 times 1 to the 3/2 plus 2 times 1 squared. So no matter what, this one will just be 2 plus 2. So this is -4 over on this side. On this side, we have 2. And when we do 4 to the 3/2, that is just saying, hey, this is really 4 cubed and then the square root of it, or square root of 4 and then cube it. So square root of 4 is 2, 2 cubed is 8, or the cube of 4 is 64, and the square root of 64 is 8. Plus, let's see, this is 16 times 2, that is 32. So now we have, not 32, we have 16 plus 32 over here. So this is equal to, let's see, 8, 4, minus 4, so we have 44. Let's try one more. Again, bring your power up to show what it actually is. We have x to the -1/2 dx. So let's go ahead and add 1. So that'll get us equal to 1/2, a positive 1/2. So we'll divide by 1/2. Now keep in mind, when we divide, we're going to keep change flip. So we really have 2x to the positive 1/2. And again, you can always drop it down and reverse it if you need to double check. So we have 2x to the 1/2. Oops, it's not x, it's 9. Minus 2 times 1 to the 1/2. Keep in mind, x to the 1/2 is just another way to say the square root of x. So this is really the square root of 9 minus the square root of 1. So 2 times 3 minus 2. So that is 6 minus 2 to be 4. So hopefully you feel a little bit better about your definitive integral and how to take those intervals.